Welcome back, Oguzhan Ersoy from Gensyn. He's been up here speaking with us several times and always been quite popular. Today he's going to be taking us through distributed learning, something quite core to everything that we do. Ozzy,
Yeah,
where would you like to
actually,
start?
thanks for the introduction. Actually, it's more on the decentralized training that we are gonna focus on, and the challenges and the problems that comes when we move from the centralized to decentralized setting. Uh,
Fantastic.
and so before I start, I will mainly talk about like the general problems, the challenges that we see in the decentralized setting, and some of the uh, topics that we have been working on, the solutions that we have in this space. And I split this talk into three subcategories. The first part will be more focusing on the efficiency of the communication. The second part will be more on the modularity of the expert training. And the last part will be robustness against the failures or the attacks of such decentralized trainings. So then let me start with why we care for the decentralized setting and how it differs from the centralized ones. First of all, in a decentralized setting, we can take advantage of the compute that is geographically distributed, and we don't necessarily need to collect all the data in one single data center. So it also allows you to handle privacy if needed, and at the same time it enables like collaborations between different institutes without not necessarily sharing the data or not necessarily also sharing the other private information, which is which we have been actually seeing in the research and also the applications more on the federated learning setting. But federated learning is one of the approaches to achieve that. And so basically, decentralization allows us to use more compute, not necessarily share the data, and also because it's decentralized, and at the same time, it's not necessarily requiring the high density compute requirement, which is what we are seeing in this current centralized data center solutions. If we look into what differs the decentralized systems compared to the common centralized ones, what we see is that in the centralized solutions, they have a uniform clusters of the GPUs, meaning that almost all the GPUs that communicate in the training of the same model, they are the same GPUs. They are connected with high-speed networks, whereas in the decentralized setting, uh, we may not necessarily have homogeneous nodes, meaning that like there could be compatibility issues that we need to solve. There could be a load balancing issues because the different GPUs may have different capacities, different memories, and then we need to take that into account to maximize utilization of the whole system. And at the same time, we because of the decentralization and the nodes may be geographically distributed, then the connection between those nodes may not be high speed connections that we would see in the data centers. It would be much less bandwidth and high latency. And in this talk, we are going to talk about how to solve these challenges when we move to the decentralized setting, how to minimize the effect of the communication, how to minimize the effect of the synchronization requirements between nodes that is also relying on the communication. And one final thing that worth to mention is that like when you move from the centralized solution to the decentralized one, then there's also a trust issue, because in a centralized solution you either trust the central authority who controls everything. If you move to a decentralized setting, then there will be multiple nodes that are involved in such training or fine-tuning or whatever the task that you are doing. Then the trust will be split among the parties, and which makes it also more challenging, because now you need to make sure that all the parties are behaving honestly rather than one single entity. So this being said, I will now start with the efficiency one. efficiency problem.
Just before you jump in there, Ozzy, can you give us a couple of real-world examples of those different types of systems?
Yeah, of course. Most of the foundation models that we see, for example, ChatGPT or Llama or the Qwen models and such, they are trained in centralized data centers. And those models, since the foundational models are basically getting much bigger and training of those models require a lot of data, we need to this training of such models require, first of all, parallelization among the data side, and secondly, parallelization in the model side. And what because of this parallelization of the data, then you are required to synchronize among the different nodes. And because of the parallelization of the model among different GPUs, then you also again need to send and receive relevant information between different nodes. This centralized setting, on the other hand, has been used actually more on the task that doesn't necessarily require so much synchronization. Like, for example, if you are solving a problem that doesn't necessarily require you to communicate with the other nodes, but if you individually find a solution that's useful, then you can use there exist such systems for a long time that has been taking the advantage of the decentralization. Whereas for the training of large models, this has not been used so much. It's also because that so far the models that have been trained were small, and it's getting only bigger nowadays that we now necessarily need to use a lot of GPUs and a lot of data. And actually, as I said in the beginning, the decentralization in the model training has been used in the federated learning, which is a subcategory of the data parallelism, where each node has their own data that they don't share with others, and they all train their models, and once in a while they share their model updates so that they can all together train a global model that performs the best. However, the federated learning was mainly focusing on the privacy problems. But here we are more looking into the communication efficiency that comes with that. So in this talk, by the way, I'm not gonna focus more on the privacy problem or the solutions, but more on the communication efficiency or the robustness problems and the solutions in the decentralized setting. Do you have more questions, or do you have a more specific question that I can answer?
Apologies, Ozzy. I lost my connection there for a moment. I'm happy for you to continue on, and I'll jump in shortly.
Oh, okay, cool. So as I said, since training such large models require a lot of data, and also since the models are becoming larger, we need to do model parallelism. In also decentralized setting, we use such parallelism methods. And in this talk, I will mainly focus on the data parallelism, pipeline parallelism, and expert parallelism methods, whereas in general, there are additional parallelism methods. However, they are not much suitable for the decentralized training because of the extensive communication requirements, such as tensor parallelism. So let's first look into the data parallelism and what are the challenges in the decentralized setting. So in the data parallelism setting, imagine that you have replicas of the full model among different nodes, and each node using the local data that they have, uh, they train the model, and once in a while or after every iteration they synchronize with the other nodes. And this is done by a standard all reduce, where all the nodes send their updates to each other, or maybe there might be a server that collects the updates, and then each node eventually receives the updated weights, and then they continue training. So because in the decentralized setting we have limited bandwidth and the latency, we want to reduce the synchronization requirements in data parallelism. And in federated learning, we already seen that you don't necessarily need to synchronize with all nodes at every iteration, whereas you can synchronize once in every, I don't know, like 10 or 50 iterations, and still you are able to converge almost at the same pace with synchronization at every iteration. And in our work, Noloco, what we did is we even improved these existing solutions with a step further by reducing the synchronization that is done among the all parties to synchronization among peers. What I'm saying is that, for example, if you are, let's say, in the standard data parallelism, if you split the data among 8 nodes, let's say, then what is expected that after every iteration, all the 8 nodes synchronize with each other. And now we know that you can, each node can do a lot of updates within their own local system and then synchronize in once in every 50 iterations, let's say. And with this method, we are saving the communication by, we are reducing the communication by 50. But what we did in our paper Noloco is that we extend this even further by reducing the synchronization among these 8 nodes to synchronization among peers. And in this way, you are not only reducing the synchronization that is required in the whole network, but also you are increasing this throughput speed, because in the decentralized setting, when you are synchronizing with all nodes, then you are limited by the slowest one among all. And if you are reducing the number of synchronization, then you can do training steps or the update steps much faster, and then the whole throughput will be even faster. And in our paper, we show that in our technique, we are able to converge at the same pace as the full as the all nodes are converging, and we are able to also save the communication. So we are not only saving the communication, but also converging at the same pace. And that was one of our works, which is called Noloco. And that was on the data parallelism part. And now let's talk about the pipeline parallelism. In the pipeline parallelism setting, you split the model into disjoint stages, where each node is responsible for their own part of the model, and then in the forward pace, they obtain the activations from the previous nodes, they do the calculations of their stage, and then they send the activations to the next node. And in the backward part, they send the gradients of the activations in the opposite order. Pipeline parallelism, as I said, because of the parties are only required to send the activations, it is one of the commonly used model parallelism methods in the decentralized setting. However, even that setting is not ideal for the decentralized trainings. Why? Because in the pipeline parallelism, every time you are uh, doing a calculation and then sending the update to the next node, you need to wait all the nodes in the same layer to have the same updates. And not only that, but also in the decentralized setting, because of the bandwidth and the latency differences between different stages, then the different stages may need to wait longer or shorter. Uh, in our paper in Skip Pipe, we take the advantage of the known resilience of the large language models, specifically transformers, which are showing that if you do layer reordering or layer skipping, then the training is not necessarily affected significantly. Whereas by doing this reordering and skipping, you can significantly improve the speed. So what I mean is that in the standard pipeline parallelism methods, the training was done on the full module, and every time the training was done in the same sequential order of the stages, meaning that first you apply the data to the first stage, and then the output is sent to the second stage until the last stage, like the standard way of doing it. In our method, what we did is that we introduced some skipping and swapping the stages, which allowed us to minimize the waiting time of the nodes to each other. But at the same time, it didn't affect the convergence of the model significantly. And that is because the transformers itself has such resilience. And not only that, but also thanks to the training with the skipping, we also noticed that the model that's trained in our method is also resilient to faults in the inference. Meaning that, let's say you want to, after training the model, you want to do inference on such model. And if you split this model into multiple nodes, again, in the pipeline setting, even if some parts of the model are skipped in the inference, you are still getting a quite valuable output. So this shows that when you do the training in our method skip pipe, then you are also obtaining a resilience on the inference. So it's the second advantage of the method. Is there any questions or comment on the efficiency part? If not, then I will continue with the modularity. So what do I mean by modularity? So the common known or used foundational models, they are generic and they are targeted to provide you a generic information and able to handle generic tasks. But maybe you may require to have some expert models that are specialized on specific domains, which can be coding, math, or translation, or whatever special expertise that you require. So normally what you can do is that you can fine-tune an existing standard model, and then you can combine several expertise together to achieve a global better model. Meaning that, let's say you have a coding model, and then there's another math model, and then there's another model that is an expert on another domain. Then you can, combining these methods, you are able to achieve a unified model that is good at all these tasks. So first of all, why would we care on such settings? First of all, training such expert models can be done in parallel, which is very suitable for decentralized settings, because since each expertise is trained with its own data, then they don't necessarily require any synchronization during the training step. Only during the inference step that they need to be combined. And then the way that it's combined is also dependent on the setting. In our paper, Heterogeneous Domain Expert Ensembles, we looked into the problem that if you want to train such expert models, then would you benefit from heterogeneity of such models? Hello, Xavier. I hear some background noise from your side. All right. I think now it should be fine. So I was saying that in our heterogeneous domain expert ensembles paper, we investigated the heterogeneity of these expert trainings, meaning that, let's say you have a limited cost or limited budget to train such experts, and you don't know how to split your budget so that you will train several different independent experts that will later on give you a unified model that is good at multiple tasks. And we show that instead of just splitting your budget equally in each expertise, it's better to split your budget with respect to the difficulty of each task. Meaning that, let's say you have some complicated tasks like I don't know, algebra, and then you have some simple tasks like uh, elementary school level domain expertise. Then, since the complex tasks require more training, it's better either to train them with more iterations, or it's better to train them with larger models with the same amount of iterations. But since the model is larger, then the learning is, or the capacity is bigger. We show that training such systems will eventually lead a better solutions, meaning that like you will have better uh, models that are able to answer different domain requirements or the different domain tasks.
Mm-hmm.
However, uh, such systems or such inferences requiring all the models to be used at the same time. Meaning that, let's say, if you trained a math model, a code model, and then there's a third model, language model, let's say, and then you have a task that requires input from all of them, how you then getting an inference from such setting requires you to use all these models, meaning that you have a significant overhead because you need to use all the models in the forward pass. So how can we also overcome such additional overhead? One method to overcome such additional overhead is actually using a mixture of expert style models. So now we have these expert models that we already trained. So how can we merge these models into one single model so that we can use just one single model for the inference? Now you can just think that, okay, why don't we just average these models? You can, and actually that performs up to some level. But the problems with such settings is that when you are just merging several different expert models together, then you may have interference of the domains, meaning that because of the just merging or averaging these models, you may lose the best of each individual expert performance. You may have a decent, maybe average, but like it will not be compatible with each individual expert because of the interference coming from the other models. To overcome this issue, in our paper, Doom, we introduced a new method. Actually, we didn't introduce the method of the merging, but like we introduced the method for the routing. So what we did is that like instead of just averaging the models, you can combine the models in a way that you keep the feed forward layers as an individual expert. So you don't necessarily interfere this expert knowledge of the models together. And then when you are doing inference, you can just use this as a mixture of expert architecture. So to be able to use this system as a mixture of expert architecture, you need a router that will route the inputs or the tokens that you obtain to each individual expert, or depending on your setting, it can be like one or multiple experts can be chosen at each iteration. So the existing methods in this space were requiring additional fine-tuning or training of such large MOEs. And in our paper, we show that you can use some closed-form solutions that will already give you a quite good solution for initialization of such mixture of experts. And in this way, we are not only able to train or fine-tune these experts independently, but at the same time, after the training, we can combine them into one single mixture of experts that will reduce the inference cost. So we are, to summarize, what we are achieving with this system is that first we are able to train the expert in parallel, meaning that like there's no necessity for the synchronization, which is quite suitable for the decentralized setting. Secondly, we are combining these experts into MOU architecture, which will minimize the interference, meaning that like we are still able to achieve the best of each individual models almost the same level. And third, since because this is an MOU architecture, the active parameters, meaning the computational cost of using such model, is also quite comparable with one single dense model.
Fantastic. Ozzy, I think I'm back. Can you hear me now?
Yeah.
Fantastic. Terribly sorry about my connection issues there. So you're looking at the speed, efficiency, obviously cost has some big advantages of this research and techniques. How is this all coming together in a way that the people listening could recognise?
Sorry?
How is this all being used and coming together or being built upon in terms of something that the people out there could recognise now, or what's being built towards?
Well, actually, this is something that we are working on as in the near future products, and hopefully people will be able to use such systems, and not only our own research but also like taking the advantage of the existing research to be able to train their own models, the models that are specialized on their own data, or taking the advantage of the other models trained by others' data. Like for example, in our RL Swarm, which is a different collaborative setting where we were collaboratively training individual models together with each other, we were able to just take the advantage of the decentralization and also to take the advantage of the compete among the decentralized nodes, whereas each node were required to do some of the basically answer some of the questions, and then they were uh, collecting the different answers, and then they were learning all together. So this is one collaborative learning method. And the expert modularity setting that I just mentioned can be used to globally train a large model or basically take advantage of the expertise that each individual node has. So imagine that you may have some special data or domain expertise, and then you train a model on that, and later on someone else trains an expert on a different domain. And with our method, you are able to now combine these two and achieve best out of two without necessarily increasing so much the cost or computational cost of using such models.
So the entire network is benefiting from it and learning from each individual
Yeah,
piece itself.
exactly. So the efficiency parts that I talked first, it was more on the setting that if you want to train one large model or fine tune one large model, and then taking advantage of the efficiency methods that we proposed that reduce the overhead of the communication. The second modularity part was more touching on like if we have different expertise, how can we take advantage of each other's expertise and combine them to achieve something greater. And the last part that I'm gonna talk, which is on the robustness. So when you move from centralized system to the decentralized system, then you may also need to take more into account the failures, because in the decentralized setting, you may have more failures than the centralized one. Even in the centralized one, you have failures. That we know. We know that training of such large models, actually most of the training cost or significant amount of the training cost has been wasted on the failures of the training. What do I mean? Let's say you are training a large model with 20 nodes, and during the iteration, let's say one of the GPUs fail to reply. Then, are you going back to the training from scratch, or is there a point that you go back and you continue from there? So all these methods are different failure recovery modes, and each of them has some advantages and disadvantages. So in the standard failure recovery mode of machine learning training, there are two ways to do it. Either you use an additional storage system that stores the checkpoints of the training, and once some of the nodes fail during the training, then you go back to the latest checkpoint and then you start from there. So in this setting, you are required to do additional storage of the checkpoint, and at the same time, you are also you are still losing some of the computation that you did, because you are basically going to lose the training that happened from the last checkpoint to the point that you had the failure. So that's why either you need to do like a frequent checkpointing so that you don't lose too much, but that will also cause you to slow down the training, because every checkpointing that you store is basically a communication that you need to stop. And
Right.
if we are talking about the large models, then this means that like you need to like this communication is also can be a significant burden. The other
Yeah.
method would be redundant computation. So meaning that if you had replicas of the model or replicas of the stages of the model, then even if some of the nodes fail, then the other replicas have the training parameters or the trained or current model weights, so that you can continue the training from that point on. But as from the name, you can understand that it requires redundant computation. So, as I said, the existing methods for the failure recovery either rely on the redundant computation or redundant storage.
Thank you all for coming along, and thank you, Ozzy, for presenting, and I will be listening back myself, and we'll see you all again soon.